Biomedical engineering is an interdisciplinary field that applies principles from science, technology, engineering, and mathematics to develop solutions to healthcare problems. The mission of the Institute of Biomedical Engineering is to expand the field of biomedical engineering in South Africa through research and development. At the Institute, we have our director, Christian Skrewe, who specializes in machine vision and photogrammetry, Reine Loubser, who does research in computational biomechanics and scientific machine learning, and Johan van der Merwe, who focuses on the design and development of endoprosthesis and biostatistical modeling. What follows is a brief introduction by each of our staff members of their respective focus areas.
Good day, ladies and gentlemen. I'm Professor Reine Loubser, and I have three research areas that I focus on within biomedical engineering. The first is biomedical fluid flow modeling, where we use tools such as 2D and 3D computational fluid dynamics to study fluid flows in the human body. For example, blood flow in the descending aorta, as we can see in the bottom right of the slideshow. But we also applied system-level simulation tools to study the interaction of the different organs inside the human body with one another using 1D simulations. The next area is biomedical-based scientific machine learning, and this is where we use techniques from machine learning such as gradient descent and automatic differentiation, along with physics-based tools to study the behavior inside the human body. Two examples is to characterize the human body's functions, so for example the health of a person's heart muscle, using physics-based learning where we combine physics-based modeling equations along with automatic differentiation. Another example is to apply these techniques for anomaly detection, so to basically predict when a cardiac event could potentially happen and giving a certain probability that it will happen in the next hour. And then finally, the last area that I focus on is cardiovascular biomechanics, where we specifically apply engineering tools to study various cardiovascular diseases, for example, rheumatic heart disease or cardiomyopathy, which are both very pronounced in Southern Africa. And then finally, we also apply engineering design to look at the design of artificial heart valves. In this slide, I've listed a couple of potential projects in 2023 you can take with me. The first project is the estimation of the pulmonary vasculature parameters using non-invasive measurements and scientific machine learning. So the current state of the art in predicting the stiffness of your pulmonary loop vessel walls, as well as the resistance to flow in the pulmonary loop, is by using quite invasive measurements. And in this project, we'll look at using only non-invasive measurements and scientific machine learning approaches such as automatic differentiation and gradient-based learning to see if we can infer these parameters without requiring invasive measurements. The second potential project would look at system-level hemodynamics modeling of the entire cardiovascular system using a one-dimensional finite volume solver that will be developed in this project. So in this project, the student will develop either a Python or a Julia-based one-dimensional fluid flow solver so that we can model the pressure drops and flow rates in the different parts of the cardiovascular system. The third project would look at the characterization of transvalvular gradients, in other words, calculating and characterizing the pressure drops across the different heart valves for different heart valve disease morphologies. In other words, looking at the flow characteristics for rheumatic heart disease versus the flow characteristics for bicuspid heart disease. The final project or potential project is looking at developing a fluid structure interaction simulation model. In other words, building a fair model of the vessel walls of the aorta, along with the fluid flow or CFD flow model of the blood flow inside the aorta, and coupling the two models and then validating the results using a mechanical surrogate that could potentially be manufactured from silicon.
Good day everyone, I am Dr. van der Merwe and I focus on endoprosthesis design and biostatistical modeling. The design of endoprosthesis, which are implants for use inside the human body, involves various fields of study such as the analysis of anatomical, physiological and biomechanical data, processing of medical images such as CT or MRI scans, geometric modeling or computer-aided design of both the patient and implant geometry, computational modeling and simulation for design optimization, and of course testing and qualification of the resulting implants. Postgraduate research topics may focus on one or more of these aspects, but the solutions we develop are always aimed at meeting real needs of the South African population and healthcare practitioners. We pay special attention to the role and interaction of the various human stakeholders and take care to incorporate their input and feedback within the design process. Therefore, students interested in endoprosthesis design may have the opportunity to collaborate with industry and surgeons alike to work on real-world problems and gain valuable experience for a career in biomedical engineering. Listed here on this slide are a few example projects. The first project is mandible reconstruction using linear and nonlinear algorithms, which basically involves creating a generator of the mandible shape from linear principal component analysis, followed by reconstructing or estimating the original shape through nonlinear regression from sparse inputs. This is useful for reconstructing patient-specific mandible geometry in the presence of large mandible defects for virtual surgery planning and implant design. The second project listed involves the design and optimization of a total hip replacement for the South African population, since the majority of the implants in use today are imported from overseas and may have a suboptimal fit. So on this project, the hip morphology must be investigated to determine a statistically average population shape, and this would then be followed by design and optimization of a functional hip replacement through computer-aided design and stress analysis. The final project is concerned with developing a framework for patient-specific TMJ design that facilitates intrapatient robustness and stability while maintaining the flexibility of the process to account for interpatient variation, all within a relatively short time frame. Thank you for your interest in our institute. If you would like to know more about biomedical engineering or about the work we do, please do not hesitate to contact us.